All right. Yeah. Is there a question? No. Okay. So one thing I want to do is actually go to MATLAB and show you question 3. That's I have several solvers, and let me just run all the solvers and tell you like what is the best way to actually figure out which solver it is. So for example, one of these solvers is forward Euler, right? So actually solver 2 is forward Euler. And for forward Euler, if you run it, 2, 3 solver 2, and particularly, let's just look at the examples we have just analyzed, right? So if B is exactly equal to 0, so basically not satisfying the first condition. So for example, if I give B is 0 and A, since B is 0, if I want the sum to be less than 0, A has to be negative, right? So if I take a 0, -1, 0 for A and B, so for any time step, and let's integrate for with 1,000 time steps and 0.01 time step size, what you're going to see is that the solution should actually oscillate without increasing in magnitude. So that's the analytical solution of the ODE. But if you run the solver, why is it so slow? Okay, the solution is popping up. Right, when you run the solver, you're going to see the solution actually increases slightly, right? If you compare the blue peak with the blue peak over here, it's actually it's increasing just ever so slightly. This is because we have chosen a pretty small time step. And in order for you to actually quickly figure out what solution it is, I mean, that's kind of a common theme I see in several of you, is that some of you actually started exploring pretty large time steps, but some of you actually started exploring tiny time steps. So exploring tiny time steps really wouldn't show the difference between different schemes very quickly, because the stability region, if you take delta t to be very large, right, then the stability region are basically very large, and you are basically zooming into a very small region. So if you choose delta t to be small, then you're pretty much looking into this area. And if you look at around the origin, then the stability region of all the solvers are pretty much similar, right? I mean, they look pretty similar. They all look stable on the left and unstable on the right. The only exception is midpoint, right, as we are going to see in a little bit. But it's really hard to distinguish different solvers if you choose a small delta t. So let's see, if we use a much bigger delta t, 10 times, and look at the solution again, you're going to find out, oh, now it's pretty obvious, right? We have an unstable solution. The solution grows from order 1 to like 200 pretty quickly. I mean, if I'm running solver 2, just by this, you're going to know that the scheme is unstable on the imaginary axis, right? And you would pretty quickly converge to the fact that it is forward Euler. Another thing is that, forward Euler also becomes unstable. It also becomes unstable when the eigenvalue approaches -2 divided by delta t. So you can also explore around this region, right? And if you explore this region, just looking at the formula, right, you can choose, for example, you can choose A. I mean, the easy choice is if you choose A equal to 0, so you get a 0 eigenvalue that doesn't really contribute to either growth or decay. Then you choose a B that is more negative than -2, right? So in this case is if I choose A equal to 0, B is equal to -2.5, okay? And forward Euler is again going to blow up. Actually, oh no, so this is when I choose a lambda equal to 0.1. So forward Euler is actually not blowing up. I wanted to choose something that is beyond the stability region with the delta t equal to 0.1, which means minus 2 over delta t is actually minus 20, right? So I should actually be choosing minus 25 as opposed to minus 2.5. So if I run it again, that's when you're going to see forward Euler is unstable, right? Grows to 10 to the 176. So these are the things you can kind of explore to map out the stability region of forward Euler. A lot of you have I chose the backward Euler for a lot of your exams, right? So if I the backward Euler is actually the solver one. So for backward Euler, if I choose the same parameter exactly on the imaginary axis, you're going to see that instead of growing from from order 1 to 150, backward Euler actually is excessively stable. Instead of having an oscillation that keeps the magnitude, and instead of like forward Euler that has a growing magnitude, backward Euler actually dissipates a system that is supposed to be oscillating without decay, without growth. So if you solve it with backward Euler, it actually grows, actually decays, right? So this is one of the things that you see in backward Euler. Another thing is that we have analyzed that forward Euler is not for very stiff systems. In fact, if you, for example, choose a small a, like minus, let's say minus 1, right? And with a minus 25, you know it is not stable, right? So we have to do 0.01 for this to be stable. If I choose this to be minus 250, then I have to be 0.001 for the forward Euler to be stable. But if I use a backward Euler, I can go back to 0.01, and you're going to see the solution is stable, right? So, and here it is a case where you can see the two different timescales easily. There is one timescale represented by the red component of the solution U2 that basically you can see the exponential decay to 0 at the very small time scale, right? At the first time step is 1, next time step it decayed to less than 0.1, and then it decayed again, and then it stays 0. The second time scale is represented by the blue solution. It's a very slow decay, right? Even over 1,000 time steps, it decayed by less than half. So this is why a stiff system it really calls for an implicit time integration scheme. Because imagine if you have to stick to a time step of 0.001, 1,000th, then even to get to this point would require 100,000 time steps. And to really see the complete decay of the blue line, you probably have to use more than 1,000,000 time steps. While if you use backward Euler, and if you don't care about the fast time scale, you can just choose a time step size equal to 1. And now you can see the red one decays to 0 immediately and see the decay of the blue line pretty clearly, right? So this is basically one of the things that you can use to map out backward Euler. And one more thing you can use is to actually choose a case that is beyond the instability region of backward Euler. So for backward Euler, let me just say this is forward Euler. And then the backward Euler is stable for everything except for this red circle. So including the whole left plane and including even to the right of the circle. So to test if it's backward Euler, one thing you can do is to choose a point that should be unstable, should be very unstable for the original ODE. But for backward Euler, if you choose a large enough time step, right? I mean, remember the size of the circle is 1 over delta t. So if you want to make a point over here, for example, stable, you would choose a large delta t, so the size of the instability region is small, okay? So that can be achieved by manipulating, again, the lambdas by, for example, choosing a equal to 0 and b to be a large positive value. If you go back to MATLAB and choose again a equal to 0 and b equal to plus 250. If you use a time step of 1, backward Euler would actually be artificially stable, right? So you can see like the solution is not blowing up. And if you use any of the explicit schemes or let's say trapezoidal rule, you would get an unstable system, right? So these are the ways you can use to kind of map out the stability region of the scheme to figure out what scheme I'm using here.